Okay, today we're going to do a short intro into critical points, critical numbers. A critical point is just the x and y value, whereas the critical number is just the x coordinate of the critical point. Well, let's look at the definition firstly. A critical number of a function f is a number c, so any number, in the domain, right? So usually we're given a domain with this when we're using them to find extrema. In the domain of f, such that either the derivative of the number equals 0 or the derivative of the number does not exist. Now, let's look at these options first of all on this graph, right? Let's look at this graph. Now, we don't have an actual function given for this, but it doesn't matter in this particular case. Let's look at this. We can already tell, we know that a local maximum or minimum has a tangent slope of 0, right? That's why we can use this to find critical points. Well, a critical point is any point at which the derivative of the function is 0. Why? Because we know that an extrema will become a 0 on the derivative, and we don't know what this is, so the best way to find it is to take the derivative, then plug that 0 back into the original function to find this point. Well, let's look at this. This has a slope of the tan line of 0, and this has a slope of the tan line of 0, right? D and C. Well, let's look at E. Well, obviously on these two, if this were straight, let's pretend it's straight. Obviously on these two, the derivative is going to equal of C and D is going to equal 0. Well, on E, it's not going to exist. Well, why isn't it going to exist? Because there's no tan line that goes like that, right? The derivative of point E does not exist in this domain. So that's an example. But is it still a critical point? Absolutely. Critical point. But it does not exist. So f prime of E does not exist. Okay. So just remember that because that's pretty important. Now, C and D, it totally does exist, right? And how are you going to find them though? Well, you're going to take f of x and you're going to derive f of x, right? You're going to differentiate it. And then you're going to take that and you're going to set it equal to 0, just like we would with just a normal function we were trying to find the zeros of. We're just trying to find the zeros of the derivative instead. And then when we get those zeros, so C and D, for example, in this case, when we get them, we plug them back into the original function to find the coordinates here and here. Now, pretend that this tangent line was not above the minimum. Okay, another thing I want to say is that you're probably familiar with local maxima, local minima, or also called relative maxima and minima. It is the maximum point of this function on an interval, right? On an interval. So absolute maxima and minima are the absolute highest and lowest points. But here, for example, this is local. Now, say that we had another graph. Say that it went like this, right? On an interval. Well, this is the absolute max. This is the absolute max. And this is the local max. Local max. So you probably remember that from, I would think, like algebra 1 maybe. And then, for example, well, these are kind of the same. Say this is lower. This would be the absolute. This would be the absolute minimum, whereas this would be the local minimum. So keep in mind that the endpoints of your given interval are not necessarily the absolute maximum and minimum. That's kind of why we're doing this intro, is because the entire sort of concept here, which is Calculus 1, is trying to figure out which ones are the absolute and which ones are the local maxima. And then also which ones aren't even maxima or minima, because sometimes a critical point does not exist. But also sometimes it does exist, but it's neither, like it's an inflection. For example, if you have x cubed, right? Say you have f of x. Say you have f of x is x cubed. And your function looks something like this. Well, when you take the derivative, you are going to find this point is a critical point, but it's neither a maximum, nor is it a minimum, nor is it a point where the derivative does not exist, because it's just an inflection point. You see, we know that these minima and maxima, we know that the tan slope is 0, right? That's how we know it's a minimum or a maximum. We know here that there is no tan slope because there is no tan line. But on this particular case, for example, you'll have tan lines here, you'll have a tan line here, but you don't have a tan line that goes 0 through here, right? That doesn't happen because, well, it's supposed to just touch one point. That's what makes it a tan line. So you don't have one. It's an inflection. And my professor said this to me, and I thought it was a very helpful way to think about it, is if you don't understand why, take any portion of this. Is there a tan line? No. Is there a tan line here? No. Like, there's not a tan line where the slope is 0 at any point on any part of this graph. Whereas if you took, for example, a portion here, yes, there's this and the slope is not 0. But again, there's this tan line of the slope 0 right here. So it makes sense when you think about it for a while. If it's a little confusing, maybe go review that. Maybe go review local minima and maxima and absolute minima and maxima. But yes, in general, it makes sense. Now I'm going to do an example for a critical number, and then we're going to find the critical point. We're going to just make it super easy, right? Say that we have f of x is x squared. Actually, let me make this clear. Otherwise, we're going to start getting a bit messy with our work. Okay, we're going to do our side work here. All right. So we have f of x equals x squared. And let's look at the graph. You don't really need to necessarily, but when you're learning, it's helpful. It's going to be something like this, right? We'll pretend that there wasn't a crick there. Pretend that was smooth, okay? So this is x squared. Well, there's obviously a local minimum here. Say there's an interval. We don't really need to know exactly what it is, but this is on a domain. This is on an interval. We want to find out what this point is. Well, we happen to know, of course, that it's 0, 0, but say we didn't, right? What would we do? Well, we would take the derivative of x squared, and it would become 2x. And then we would say the derivative of x equals 0 and equals 2x, and we would solve for x and find that x equals 0. This is our critical number, not our critical point, right? This is our critical number. So we know now that at the point x equals 0, the derivative has a 0, but the original function, x squared, has a minimum or a maximum of some kind or an inflection point, right? Okay, well, now we don't know what that point is on the original function. I mean, we know that on the derivative it's 0, 0, but we do not know what it is on the original function. So now we're going to plug 0 into f of x, and we're going to find that f of 0 is 0 squared, which is 0. And now we know that our critical point is 0, 0. And of course, we look at the graph, and we kind of already knew that, but you can't take things for granted when you look at graphs either. I mean, for all you know, like if this function was slightly different, maybe it wasn't on 0, 0, you know? Maybe it was on 0.10. I mean, you're probably not doing that at this point, but you can't just take it for granted as the point. You have to do the math. And so yeah, that's really the most rudimentary sort of example. But you can apply that, and I'm going to do some videos on how to find critical points. And I hope this helps.